I put a couple of links in the slide deck so you could have some background material, since I only have 25 minutes, so it's not really possible to go into all details. My name is Hannes Tschofenig. I work for ARM. ARM stands for Advanced Risk Machines. You may have heard about the company. It's focused on development of processor technology, but doesn't actually produce processors as a company itself. Doesn't manufacture those processors, but instead those processors are developed and built by other partner companies like Freescale, Nordic Semiconductors, Texas Instruments, and so on. Okay. So I would like to start with, and keep that very brief, on what we think about Internet of Things as ARM, simply because it's a term that is very fuzzy and vague. So every time you hear someone else talking, they have a very different spin on it. It's quite natural because every company tries to use sort of this hype term and put themselves into perspective of that technology or that conversation. And so just to know where I'm coming from. So I'm seeing a lot of sort of press releases recently on companies releasing all sorts of technologies that relate to IoT. And here's one from Ubuntu, where they focus on a new, what they call IoT operating system. And as you can see, like from the requirements, it requires a fairly powerful processor with 128 megabyte of RAM and 4 gigabyte of flash. And that's quite substantial. So it targets definitely a different type of system. Something that you would probably find in maybe a modern TV set, but not necessarily in a smartwatch. Even more recent, if you look at what Google announces, they also have came up with the operating systems, like maybe 50 other companies who did something similar. And if you look through the details, it's actually, and it talks about Android, and for those who are familiar with Android, know it runs on top of Linux or a version of Linux, and it uses ARM A-class processors. And that's where we sort of make the differentiation is ARM produces different type of families or develop certain type of families of processors, and these families make a difference in terms of what is available with the hardware. So I'm talking about the devices, not what is happening in the cloud. So the devices or the device capabilities matter for what we are talking about here in terms of what protocols you can run on those devices, what resources you have available, and what not. And so I pick here as an example a smartphone which typically has numerous processors in there, and like your car would have, and many other devices. And so most of the companies focus on A-class processors, running full-blown operating systems like Linux, or your Raspberry Pi, which also runs Linux. And those have all the features that you would find on your desktop PC in terms of memory protection and etc. And it's fairly easy to get, as a developer, something working on these systems. Of course, you can always shoot yourself in the foot by just ignoring sort of common advices, but it is state of the art. People know how to use Linux. They can run software update mechanisms like a package manager and so on and so on. The story is, however, a little bit different if you go to a sort of a lower scale devices and devices or processors that use different sort of, they conserve energy better, have fewer capabilities, and obviously cost much less. So those would be particularly, and that's the focus of my work, is on the CortexM class processors. And those are, like Paul just mentioned, a few examples, like many of those variables would use CortexM class processors. And that's what our focus is in terms of IoT, working on or helping developers to make it easier to sort of get applications running on those processors, secure, and with a short time to market. And it's probably sort of needless to say that there are different types of processors because they're just even in that class because there are different needs. So you have sort of the range of devices is quite broad, and so you may need different capabilities. But I won't go into any of those details. But if you are like many of the startups, they have to bring along different expertise. On one hand, they need to have software expertise because they need to write the code to actually do some intelligent stuff with those devices. But then they also need to have the hardware expertise because they ultimately need to work with processors, put something together, a printed circuit board, and wire things up, and so on and so on. So what you would typically find on those devices is a range of different limitations or constraints. And I took some of those from this nice publication, RFC 7228. And so you, depending on which constraints you have on your device, and what the purpose of your device is, you will obviously face some issues. So like constraints regarding RAM usage, flash. For some of the variables, you care about power consumption, energy efficiency. And also different low-power radio technologies, short-range radio technologies, like Bluetooth Smart, like this Zigbee IEEE, which is based on IEEE 802.15.4. Those are radios which have a very small frame size, very often high packet loss. So it's sometimes difficult to work with. But if you have, for example, if you want to wire up or connect these luminaires up there, all these different ones, connect them to the internet because you want to manage them centrally, for example, or from remote, as some companies are already starting to do, you would connect those, for example, using a 15.4 radio. But you will obviously have lots of them, so you would potentially have a multi-hop network here. And then you think about the whole building. That's already a fairly complicated setup. And needless to say that this needs to come with a cost reduction. Because otherwise, you can't put sort of like a $100 sort of PC essentially inside the light bulb. People would get a little worried about the cost. And the cost can actually be quite tricky to figure this out and to determine on where it would be best to actually save cost, on which the hardware parts, energy costs, but also development. Many of the companies try to build everything from scratch. That costs a lot of sort of in terms of development. So there's a link to a webinar that a colleague gave to one of the working groups in the IDF I chair, to the ACE working group, which I will briefly mention later on again. So it's something for a hardware developer, for someone who develops a real product, something to take into account when doing these type of things. Here's an example. Won't go into details, but just to give you a sort of an idea on what type of scale we are talking about. Like we're talking about a processor that has 30, 50 something megahertz, a limited amount of flash, let's say 64 kilobytes of flash, or 128, a fairly limited amount of RAM, and still a lot of capabilities. Also offers hardware encryption and so on, and random number generators and lots of different protocols. But at the price, even with these low volumes, for higher volumes, if you want to produce in like 100,000 or more, you actually need to talk to the manufacturer, and you would probably get 50% off. So we're talking about €1 for these type of chips here. So it's something to keep in mind when talking about applying many of the protocols that we've heard of during the conference, when applying them to those devices, because there may be some issues in terms of size, CPU capabilities, and so on. It's still possible or it's very much possible to do all the crypto, but still something to think about during the design. So it's not just take the existing stuff and run it as is. You take OpenSSL and then run it on these devices. That won't work for sure. So you have to go through some additional thought process and development work. So what does that mean in terms of security and securing those devices. And as someone who worked very much on this internet security and who is sort of an advocate of reusing existing security mechanisms for the IoT rather than recreating something or building custom security solutions, it's always good to remember on how the internet sort of standard story actually looks like. If you look at this sort of like different categories or different pillars, there are different communities behind those. And they all need to work together in order to produce a reasonable solution. So there's not one single party that does everything, at least on the internet. Even with some of the IoT companies, they think they can just do everything themselves, which then typically fails. So you have the guys from the crypto community working out the primitives, typically in a very long, multi-year process, often competitions like the NIST competition and so on. And there are issues like people run into over time is like the researchers make some advances in crypto analysis and break certain algorithms or weaken them over time. So the algorithms age. You need to think about the right key sizes and these type of things. Then you have the standards community working on protocols, and they sort of build take these cryptographic primitives and munch it together into various protocols. And you've heard various talks about OAuth and SAML and OpenID Connect, etc. already. And that's what that community does. And of course, mistakes happen there as well in terms of complexity and other things. But then the story is not at the end, of course, because someone has to implement those protocols in a secure way, because you can still have buffer overflow problems. You can still have usability problems. So you need to take care of those as well. And everyone remembers the OpenSSL story with sort of the poorly tested code, which then led to the Heartbleed attack. And finally, you have these different communities who often implement these stacks. But then you need to have the companies who deploy these technologies, or many different technologies together. They need to do it in a way that it's also secure. You need to, for example, a common mistake is to keep debugging ports enabled, which then allows hackers to just extract firmware, extract keys, like connect using a root shell, no passwords or no security settings enabled, and so on and so on. So all these things need to work together. They need to line up in order to have a secure solution, not only for the internet, but also for the Internet of Things. So it's actually quite a complicated task for most people. So how do you then actually do that as a company to develop something secure? So of course, and this is taken from a talk I gave with 2 others at the last IETF meeting, and there's a link to the recording of the talk, which was organized by the Internet Architecture Board of the IETF, and it talked about we looked at different types of attacks and for IoT and tried to categorize them, try to learn a little bit from existing attacks, like you would do in like with web, for example, web attacks as well. You would hopefully don't make the same mistakes that other people did already. You would also follow what I call design patterns. Is simply models, patterns from a software engineering point of view, things that worked out for others in terms of like developing the overall system. You would take those into account. Presumably there's software so already available, so you would follow those. That's also in that talk, so I won't think about this here. But you would, on the first 2 items, you would definitely want to take existing security recommendations into account because others had looked hard into this and tried to come up with those. But also, you would look at these, the threat analysis, classical threat analysis, whenever you build something. Of course, there's always these specifications, like IETF specifications, others. They give you some good hint on what you should be looking for in terms of threats. But then as you develop your specific solution, you may have some additional things that you need to worry about, or some other undescribed threat may not be applicable because that context is not known at the time of writing the specification. What as a summary, without going into the details, and there are lots of examples that we collected, what you can learn from these attacks is there are sort of 5 common categories of problems. No software update mechanism available, or it is not used or doesn't work. Key management missing, so you basically pre-provision keys to all the devices, the same key, classical mistake. Missing or inappropriate access control mechanisms, not only for consumer appliances where you think that users wouldn't be able to manage those anyway, but also for industrial systems, industrial control systems, the same story. Missing communication security, or usage of some pseudo-crypto mechanisms that people come up with because they think that the devices are incapable of using modern crypto. A lack of understanding of how the hardware actually works, in my opinion. And then there's also this, what is maybe different to many of the other attacks that you've seen on the web is sort of like the physical attacks. And I find them personally quite fascinating because even if you have a perfectly secure cryptographic algorithm, if you have attackers with physical access, they can sometimes break those algorithms in almost no time. So those have to be taken care of or taken into account during the threat analysis. And this list very loosely conforms to what this Open Web Application Security Project had been doing, OWASP, for those of you working in the web space. I'm sure you're familiar with that community. But getting to the more to the identity side of things, beyond sort of plain security, a colleague of mine here always likes to draw this picture of relationship management, and Paul mentioned it already earlier in his initial talk. So you have devices that you need to manage, but you also have users and services, and they somehow all need to go together for most of the deployments. So for some deployments, it maybe things may collapse a little bit because it's simpler because there's only one service or only one user, but for many of the consumer services or industrial applications, you have many different devices and users who have different rights to access certain things during the overall life cycle. So in terms of identification of these different parties, I think the most interesting one and most confusing one is the devices. And there people talk about all sorts of identifiers, but we like to tell our partners that they should use some cryptographic identification techniques, whether it's a certificate and the corresponding private key that gets provisioned during the manufacturing process into the device, or whether this is a raw public key for which the technologies also exist, doesn't actually matter. But obviously these cryptographic techniques provide much, much better security properties than just having a serial number, just from a clonability point of view. And I wasn't supposed to have a, I hate this animation. Oops. Our co-workers of mine had been working on specifically the device management aspects in standards organizations to actually come up with a solution, standardized solution to that sort of triangle. And I'm highlighting the part on the top, which is referred to as bootstrapping. It's a key management solution to actually distribute keying material on the fly to those devices, and along with access control information, so that those devices then are sort of provisioned with information on which services or where to upload the information, what keying material to use, who is allowed to access that information. So you don't want to pre-provision this up front or keep it the same on all devices, but instead you want to have each device managed individually, each device with its own credential, and each device always sort of, when you change configuration in the backend, use different servers where you upload things, then those should be provisioned dynamically. And this is what the Open Mobile Alliance with the lightweight machine-to-machine communication protocol actually does. It does lots of other things that are also important, but probably not that important for the for this meeting. So the specifications are finalized and available, and we've been using them for various tasks, as you can see. That, however, was only a starting point. That was work that was done a few years ago, and it was finished not too long ago. But there's also newer work that I would like to point you to that tries to not only focus on the device management, as I had shown you on this triangle, but then also takes the user into account, link up the device with the user and the service. And that's what this new working group in the IETF is supposed to be doing, called ACE working group, Authentication and Authorization for Constrained Environments. So it's, as the title says, it focuses on this IoT case and specifically sort of the authorization aspect. The work has been started last year, mid-last year, so it's not finalized yet. We haven't chosen any solutions yet at this point in time. You're, of course, welcome to join the discussion and the group. There are a few things available already. A fairly lengthy use case document that looks at exactly these challenges that occur when you have more complicated real-world use cases with containers, shipping containers, and different players in the ecosystems and have access during that life cycle, industrial use cases, and as well as home automation use cases, etc. There's also an architectural specification that outlines on how the different parties interact. And hopefully at the end, when the work is finished, we're going to have a protocol mechanism that allows us to tie these, the user identity or the device-related aspects with the user components together. So for example, I just mentioned it here. So if you have an employee in an enterprise network, you most likely have an identity management solution already to manage access to various resources for that user. And so adding the physical devices, for example, the door lock, light bulbs, and so on, shouldn't be revolutionary different. You should be able to reuse the same backend infrastructure, the same protocol mechanism, at least to a large extent, and then tie them into that ecosystem. That's what we are trying to get to, and this is the working group I co-chair. And we have solutions that talk about UMA and OAuth, but there are also other ideas entertained, Kerberos-alike concepts and so on. So we'll see what comes out of it. So what are we doing to contribute to all of this beyond participating in the standards work? We have a platform, what is called embed.org. If you go there, you will see it. It's an online IDE compiler in online IDE. It has a compiler in the backend that produces code for these different IoT devices, and I have a few with me in case you want to take a look at them. And we've been running this already for several years. We have the many different projects being worked on. People produce commercial products with it, but it's also used by students. It's something that is supposed to be easy to use. Plug in your demo board, you type in the code, you reuse existing libraries, and compile it. We have an operating system that we offer, and it's fairly painless. So when I teach classes at the university, in 1 hour, students are able to write their own Bluetooth smart heart rate sensor. So it's not terribly complicated. So that's what we do today, so you can do that already. In what we are working on right now with some of our partners is to extend this whole architecture and refine the operating system, what we call Embed OS, and to provide sort of better security mechanisms inside that operating system. So, and the operating system will be free for everyone, so you can use it. It will work obviously with ARM-based architectures, but it will also have not just the bare operating system, but also the communication protocol stacks, because you would think normally that these IoT devices, since they're small and so on, there's not that much code. But there's actually a lot of code if you want to connect them to the internet. If you just think about the security protocols, you think about IP, you want to have some UDP co-op. Someone mentioned MQTT earlier today in the keynote speech. And you want to have all these software update mechanisms, etc. So there's some stuff. But then, of course, you need to have the server side available as well. And since those are open standards that we are using, you can, of course, put your own there. So with my students, I use an open source project to just have them configure something. But of course, you can also use commercial products for that. And that's something we work together with lots of partners, not just with silicon partners who then ultimately produce the hardware for those devices, but also with cloud partners, and some of them are also in the room, telecom operators, etc. And this is how, sort of on stack-wise, some people prefer the stack notion. So you have, on one hand, you have the device, sort of the lower part is the device with the protocols I mentioned. Then there's lots of different things. If you just think about the radio technologies that exist that people want to use, everything from sort of a more power-hungry Wi-Fi to a really low-power Bluetooth Smart or this Zigbee technology. And then on the server side, you need the equivalent, everything open standards-based, nothing sort of proprietary stuff. So in a summary, what we've been seeing is that developers often have, it's like sort of innovation really starts with many of the smaller shops, if you will. And needless to say that they have a limited number of resources. So they know something very well. They have an idea about the products. You see lots of Kickstarter projects and other companies who develop IoT products, some of them shown by Paul previously. And they may be very good at hardware. They may be good at design. They have some new ideas. But they often don't have sort of the full range of ideas. They are not internet protocol specialists. They are not going to write a new HTTP protocol stack and so on, or security protocol stacks. And hopefully they don't even try to. Because we want to provide them these sort of the software stacks and this for the devices for free. So, so they can actually use the same stuff during prototyping and also then subsequently for the real product. So no difference. The prototyping port is probably easier, obviously, to work with because it's you get it off the shelf, and otherwise you have to build your own port. But along with this comes then not just the IDE, but also the operating system, the protocol stack, and also the security foundation to actually deal with some of the problems that we have been seeing with existing IoT products. Those are some of the attacks that really remind you to the early days of the internet, sort of very basic mistakes. And of course, we are also participating in these standards organizations, and hopefully some of you will also join that work, because I often hear in press articles or from others that we don't have enough standards. The problem with IoT is standards. The problem is that they don't know what the standards are and not participating. That's the problem, but not that there's a lack of activities. And many of us also in the room are participating in those, but we need more to help us work on those specifications, finalize them, and advance the state of the art. Good. That's all I have. Thank you.
You mentioned microcontrollers and the cost model associated with those. A lot of use cases seem to be throwaway devices, like putting a microcontroller on a filter that may only have a lifetime of 3 months and then needs to be replaced. Are there any standards being worked on in IETF or elsewhere where the choice of microcontroller and the upstream control framework allows for a standard token type? Because you may not even have encryption capability on that microcontroller, just a Wi-Fi connection, as an example.
Just, did everybody hear the question? Bob was questioning about IETF short-lived things.
IoT.
Yeah. So overall, so when okay, I'll try to go back a little bit. So we focus on these type of processors, and even the lowest class runs crypto. So all of them can do public key crypto. These are 32-bit processors, and they're really competitive in price because it's actually fairly counterintuitive, but the economy of scale provides you with sort of really low prices for actually fairly powerful processors. So someone who tells me that, well, every time I hear that it can't do crypto is, I don't know what they are using. And they shouldn't be using it. It's probably more expensive than this. But of course, you may have different requirements in terms of, for example, if a user interaction, you may not want to wait for the time till a crypto operation is finished. So there's some of the chips come with hardware crypto, some others don't. And so even if it's throwaway, you may want to have the mechanism to actually replace things on a periodic basis. So the shorter you keep a specific secret, the more you can actually reduce the key size quite naturally. So if you want to have a device running for 20 years and still want to be secure, then the key size needs to be longer. And so the mechanism, the OMA lightweight M2M mechanism, would provide you with that capability to actually sort of do the key management, get new keys as you need them, and then basically start from scratch. Even distribute, it supports public key crypto as well as symmetric key crypto. So it actually accommodates for a very wide range of use cases. Yeah. But I should have included, and I will do that, include the pointer to the performance analysis that we did. I also submitted it to a workshop that will take place in July organized by NIST on lightweight cryptography. In my position paper, I basically argue that there is no need for lightweight cryptography because the stuff that we have is already lightweight.
Any other questions? Hannes, you argued for devices to have crypto keys rather than merely identifiers. Do you see them using those private keys on their API calls, on their, when they report data, or some different model?
So I would like to see that in various places. So the first one is when the device talks to the management server, for example, to get the firmware updates on a regular basis, or maybe gets firmware updates on a regular basis, then it needs to authenticate itself. It may also need to verify or even decrypt the firmware updates that it gets from that server. So it will have to use crypto there. Okay. The other thing is, once it then talks to application servers to actually upload the data, it will also have to use some credentials because you want to make sure that on the server infrastructure that you don't get data from random entities where there's no correlation between the device and the actual place where the data comes from. So I vision it to be used there as well. Okay. And the use of public key crypto is or our favorite because of course, it's more heavyweight, but on the other hand, it also has better properties when you think about the entire chain of companies that are involved. So fewer people, fewer companies will see the secret. So ideally, we want to have the keys generated on the device itself and never leave the device to begin with.
Quick question.
Do these kind of boards have a secure element or some other way to prevent keys from leaking if the attacker has physical access to the device?
So it depends on the board. So some of the devices actually have those capabilities, but you as a company, you would have to, or as a as someone who designs it, you would have to explicitly decide about this. So what we are working on with this, this operating system, what it does is it uses, so it's a microcontroller as a system on a chip. So it's everything on the chip. So the RAM is on the chip, the flash is on the chip in one package. So it's not like an A-class processor where you may have everything on a package, but it's still, the RAM is a regular DRAM. It's actually separate from the chip. So you could actually look at the communication between the processor and the DRAM to see what's going on. Of course, at some point in time, the key will be in RAM, needless to say, if you don't have a secure element. So in these MCUs, the architecture is already different to begin with. So, and the operating system, we are using memory protection capabilities that come with these M-class processors, and we mandate them for the upcoming version of our operating system, which allows us to basically create a sort of a microvisor at the bottom layer that controls access to those type of secrets. And even if you have a buffer overflow at one of the application code, it will not be able to get access to the secrets. So in that sense, you could, it's still different than a secure element from a sort of conceptual point of view, but it provides somewhat similar capabilities. The implementation that we are using for the crypto stuff is taken from a company that we bought, Polar SSL, and which has been hardened for various different security aspects. But it increases the cost of getting access to those secrets. But of course, it's not, you can't guarantee that someone would not be able to do that. But to combine with this key distribution mechanism, the situation is much, much better than today in the sense that if you hack, for example, a light bulb, you will have the key of that light bulb, and that's it. So you have the key of your own device, which in some sense you can argue, okay, it may be a disaster. If someone breaks into your house and then does a side channel attack on your light bulb, they will maybe get the key. But they will not get, for example, the keys of all your products, for example, which is a mistake that happened numerous times already when people use the same key for all devices, which of course simplifies key management, but
yes.